Okay, so question 2 about conservation of mass again. This is a more wordy question rather than a calculation question, so I'll try and use some diagrams to explain this one. But it's asking us what is meant by the term conservation of mass, and to give your answers in terms of the atoms taking part in a chemical reaction. So if we imagine then that we have a particle A having a certain mass, so we'll just make these numbers up, say 5 grams. And if that is going to react with particle B, and we'll say that's got a mass of 6 grams, then what the law of conservation of mass would suggest is, in a simplistic sense, that the mass of the product is going to be 11 grams, because we have to have 5 grams of A, 6 grams of B, and so when they combine, all that mass must be present at the end of the reaction. So if we go from the left-hand side of the equation to the right-hand side of the equation, that mass must have been conserved, hence conservation of mass. And what must have happened is A and B must have combined in some way. We won't give him much more detail than this, but should have combined in some way to give us a compound, a new particle with an A and a B in there. Again, in the same ratios as the A and B on the left-hand side. So, for example, if there was one A and one B, there would still be one A and B on the right-hand side, chemically combined in some way to give us that mass of 11 grams. If, for example, we'd had 2 lots of A, for example, that would have given us 2 lots of 5 grams, and so the final mass on the right-hand side might this time have been 16 grams, and there might have been again 2 lots of A within that compound, giving us an A2B type compound. But in terms of absolute numbers, you'd be able to add them all up, and everything that you started with, you must end up with. And so moving into question 2, this then gets taken a little bit further, because what you're doing in an actual experiment is weighing the mass of the powder beforehand. So if we had a beaker with some solid in it, then that would have had a mass. And if we do the reaction, so that's the zinc there. So again, we'll just make some numbers up. We'll say that's 10 grams, and we'll do that reaction. And we may have found out that it weighed afterwards, should we say 12 grams. Again, making these numbers up, but that has gone up. So what this is asking us to do is to explain why that has been the case. And because this was zinc to start with, we know that this is now zinc oxide. There has been something added to that, and to allow for that 2 grams increase in mass. And the equation tells us that that must have been the oxygen, which had been present presumably in the atmosphere, has come from the air. And so the 10 grams of zinc that we started with has become 12 grams. We've not, and this is a kind of experimental issue whereby we haven't really added a mass of oxygen. We didn't weigh anything out. We just heated this thing up in air, and the mass went up. And that's because it's managed to extract the oxygen from the air to the tune of 2 grams. And so the mass has gone up, because if we were to visualize it, we would have theoretically added a little beaker of oxygen, and therefore that would have had a mass of 2 grams, still allowing us to combine those masses, and again allowing us to adhere to conservation of mass. It's just that sometimes you get additional mass from somewhere else that you perhaps didn't do. And also for this one, what we've got to kind of try to appreciate is that oxygen, although it is a gas and essentially floats around in the air, does actually have mass. And so when that's combined with something and they're making a solid, you see a little s in brackets there, when you're making a solid, that's going to provide mass because it has substance to it. Even though it might be a gas in the air, it will still have some mass to it.